Thank you so much for the invitation for allowing me to talk in the seminar series. And I always like my work is like on such like generalized models. So a lot of times I feel that I'm like really in between of like many different fields. So hopefully today what I'm going to talk about can be give people like can be people like can make people in the biophysics community like find something interesting, and then there can be like some common grounds. And if you're interested in my method, please feel free to let me know. I'm always happy to have like more people using the tools I'm using. And also it's really amazing to follow to give my talk after Miranda, because I also care a lot about geometry of particles. Yeah, so today my talk is on design parameter interactions in self-assembly. And so I always kind of feel like when I talk about self-assembly, I always want to find a lot of examples for people to look at, like for self-assembly. So, okay, kind of personally, I have like a pretty broad definition on what self-assembly is. And I really feel like self-assembly a lot of times it's like we're thinking about some local interaction plus noise, which make me feel like self-assembly usually is something that you'll observe on like a lot of different um, scales. So from like the smaller scales, we have your virus shells or protein cages that can self-assemble into this really nice like some self-limiting form. And so like this little clusters. And then if you use like biomaterials, but then you kind of like put in like human interventions, we can have all this like really nice DNA origami tiles, and then they can assemble into this like really nice big structures. And on like slightly more larger scales, we have your Clodo particle. So this is like one of my favorite papers about Petri particles that assembles into a Kagome lattice. And then you can also have all this like different shape polyhedras that can assemble into like nice large lattices. And so moving on into skills that we can actually interact with like our everyday life, that you have all this like nice robotic swarms that by having some kind of local interactions, they can go into like different form different shapes. And then of course, I started with some bio examples. I need to finish with one. So here we have like all this like really nice bees that they have like they form in this like swarms, and then they can have like different interactions and have like different shapes. And this also like happens a lot in fire ants as well. And then there's like all this like nice series of paper talking about how a collection of fire ants that they have like the viscosity of honey. Okay, so here I'm just like showing a lot of like different examples of self-assembly. And then like for me, that the thing I kind of really care about is like how do we design self-assemblies? How do we go from like our building block local interactions and plus noise to some structure? And right now, basically there's like two different ways you do self-assembly, like thinking about design. So the first one is like the forward approach, where basically you just think about like this are like our building block space, and I'm just going to do a lot of simulation or a lot of experiments to observe like what kind of different structures they can form at the end. So here's like for me a nice example where they were just like looking at different shapes, and then they're able to kind of like you or screen out like use like three different parameters to describe this like family of shapes, and then they're able to run all these different simulations, and then kind of look at what are their final structures. And then they found a lot of different really nice structures. And so, but there's like some problem with this. So one thing you can see is that in like the leftmost picture, you see that first we're not really dividing this phase space evenly. There are like regions that people need to spend a lot more time in because like there could be something that is more interesting, and then there are like regions that like the patches like the kind of like the phase space, so they're like a lot more zoomed out. And this kind of gave us sort of idea of like some disadvantages of for assembly is that we don't really know where the interesting regions are. And then there's also all these gray regions. Like right now in that paper, they didn't observe any structures, but that doesn't mean there's nothing forming there. And so they're also kind of like we're searching a needle in the haystack, and then we don't even know whether there is a needle there. Maybe we just like didn't search hard enough. Yeah, and of course, like in experiments, you can also do the same thing, that there are like coded DNA coded nanoparticles that can also assemble in this like really nice different structures. And then if you read a bit more, like they can assemble really amazing structures, but a lot of times like it's really depending on the annealing protocol. And for like this nice large crystal domains to form, sometimes like the annealing time can take up to weeks. So because of all this, like and also like for design give us a lot of like really amazing like inspirations that people think about, like how can we do this better, and how can we like search needles in like a whole needle stack inside haystacks. So there is kind of like the inverse approach. So it's more like we first have some kind of target we want to hit, and then we ask, okay, what kind of building blocks interactions like we need for that. So there are numerous like inverse design approaches for a lot of different self-assembly systems. So here where I'm just like going to highlight a few approaches. So the first one is like this kind of like landscape engineering. So where they first like really explore the potential like free energy landscapes like that all these like particles can form, and then they ask like how do we design the particles like to hit like whatever structure they want. And then there is like alchemical Monte Carlo. So this is like more in this picture it's more targeted into like shape particles, but then later on there will always also able to do it on like different pair potentials, and kind of like this is like a random walk in the space of asking like how do we evolve our shapes to fit like the structures you want to assemble. Yeah, and then there's like also relative entropy method where you kind of like use the signatures from your GFR, your radial distribution function, and ask, okay, what kind of pair potentials you want to have that can assemble into the structure you want. Yeah, and then lastly, there's like kind of design engines, sort of like a bias walk to see like where it can get to like the result you want. Okay, so these are like a lot of like nice inverse design approaches, and most time like when people think about inverse design, they're like thinking about like this optimization problems that they want to find like the optimal set of parameters that can assemble something. But so I kind of like I want to move slightly like one step forward of it, because we're also in like the space of like soft and biomaterials, and a lot of times like we have a lot of noise in the system, and there's like a lot of degeneracies in like what is a good enough solution. So I want to kind of like think about like what happens beyond the optimal parameters. And then like, or is there like actually just like one optimal parameters, or there is a set of them, or some kind of landscapes of the optimal parameters? And then kind of also think about like, can we learn new physics along the way? Okay, so this is kind of like the kind of questions I want to ask myself and ask you, and when we're thinking about designing something. And so what are the tools I'm going to use for all this designing? And so the tool I'm going to use is something called molecular dynamics with automatic differentiation. So a handful. So here you can see a picture of like just like some illustration of a neural network. And so in a way that we're taking the tools from machine learning and artificial intelligence that allows us to train neural networks. But instead of having a neural network, we're going to replace it with a molecular dynamic simulation. So we're going to have like similar to a neural network, we're going to have some input parameters, and then we're going to run an empty simulation, and it has some like output parameters, and then we're going to measure like, okay, how good are our output parameters, and we're going to back propagate the whole thing. So this way that we can use gradient descent to ask, okay, like how should we update our input parameters in like this like model, and then think about like and get to whatever final structure we want. So the toolbox I'm going to use is called JaxMD. It's fully open source, and then you can find the link here. And if you want like scripts to run MD simulations on this, there's like a bunch on the website. And then I also have a bunch of like tutorial scripts, so like feel free to reach out to me. Okay, so and kind of to like answer the question I just asked, I'm going to use I'm going to use a class of models called patchy particles. And So this will be kind of like the generalized model I'm going to use. And the reason I like to use this model is like it really kind of like is a really nice tool to represent a lot of different materials. So here kind of just like showing all the different shapes and geometries and interactions like your particle can have. So here we're like looking at synthetic particles, but of course you can imagine this being mapped to like proteins and DNAs and whatnot. Yeah. And so we can kind of like coarse grain out all this like building blocks with like different geometries and interactions. So you can imagine like a collection of like different type of patchy particles models you can have. So and then this can be used to model a lot of different structures. So here, like at the end, I even show like a very complicated patchy particle model. You can sort of see that it's like coarse grained out from a protein PDB file. Okay, yeah. So, but for the interest of this talk, and then right now what I'm doing with JaxMD, I'm going to use a very, very simple model. So the model I'm going to use is like just this patchy particles that have like two different patches on them. And but already you can see there's like a bunch of different parameters we can tune. So here we have R, that is the radius of the center particle. So that's kind of like the decides the shape of the particle. And then we have A, the radius of the patch. So that kind of decide like how precise our interactions will be. And so theta will be the patch opening angle that determines like where the location of the patches will be. So kind of decide like kind of what structure in like one of the parameters that decide like what are the final structure it can form. And then we also have E, so that is a patch binding energy matrix. So here that our goal is like we want to assemble a finite cluster. So like especially the two clusters we're going to look at is like a triangle and a square. And in this model that you can see that in order to form a self-limiting or self-closing structure, that we need to favor like the green patch and the orange patch to bind to each other. And we want to reduce the interactions between green patch and orange patch. But in optimization, we don't want to bias towards that. So we're going to just allow everything to change and then ask, okay, what are like the final optimized structures, like the optimized parameters. Yeah, and we kind of choose this model is also in the sense that all this like self-closing like clusters, like this definitely is like a very simplified model, but hopefully later on we can build up to it and to design something that is like 3D and in more complicated shapes that can be representing and thinking about like how this like protein self-enclosing shells form. Okay, so this is our model. And then, so how do we actually do the optimization? So basically the optimization simulation flow looks like this. So we first have our optimization parameters that we introduced in the last slide. And then we're just going to run like a standard for the molecular dynamics simulation. And then we're going to observe the final structures. And then we're going to design a loss function that measures our final structures and to see how close or far away that we are towards like our goal. And then we're going to take gradients of this loss function in respect to the parameters we're optimizing. So here it will be like the binding energy and the location of the patches. And then we're going to update the parameters and we're going to keep going in this loop until it converges. Yeah. So one of the questions like people always ask me, especially from like the more like neural network training community, is that like they don't believe that I can actually thread through the whole simulation. So here I'm also going to show you like sort of like a pseudocode version to demonstrate that how these are all interconnected with each other. So kind of like you can imagine that we're defining a function that is our forward molecular dynamics simulation, and these are the input parameters for that function. And then after n steps of MD simulations, we get some final structure. So now we have a mapping between the final positions with respect to our input parameters. And then we can put these final positions into our loss function. So this way that we can basically now loss function is a function of the final positions and of our input parameters. So this way that we're able to take the gradient of all the losses. Yeah, and this is kind of like how a typical optimization run is like performed. Here you can see the change the change in loss in purple, and then the change in patch opening angle in orange. And at the very beginning, we have some random guess, and then the location of the patches are not great, and you can see like we don't have anything assembled. And then in the middle is like getting better, and the end that the loss function decreases and converges, and our patch opening angle also converges. So, and you can see that we have a lot of structure that's successfully assembled. Okay, so when we first developed this platform, we were kind of just like wanting to use this model to see like to demonstrate that it works. And so and there we only did like kind of like we arbitrarily choose one patch sizes, and then we just like ask, okay, what are like the good patch opening angle for it? And so and then we found something that is like really interesting. So like the final particle, we found that the patch opening angle for like assembling a square that is actually like 100 degrees instead of 90 degrees. And then we're like really curious. We're like, is this like actually correct? So we actually run a lot of floor simulations and said, okay, yes, it is actually that 100 degrees will want to form squares more. And then I think roughly 70 degrees will want to form triangle more. So already like here we just like did like a nice demonstration. We already found that we already learned something that geometric solution is not the best for self-assembly in these finite clusters. They want to have like a slightly bigger opening angle. So to build on top of that, and now we want to actually just like ask, what happens if we also change the sizes of like the patches, like because like in particle synthesis that you can never have exactly as precise of the patch you want, or like the location of the patch. So we want to think about like what are the tolerance on that, and does like having like a really big patch or a really little patch like influence assembly? Yeah, so we moved on to like also like have a systematic examination of like what happens when we change the size of the patches. And here where things like if you make the radius of the particle bigger and make the radius of the patch bigger, then like you're basically having like a similar particle. So the parameter we're going to look at is going to be the ratio between A and R. Okay, so we did that for both triangles and squares, and we found some like really interesting results. Okay, so this is a patch opening angle versus like patch size like results for squares. So what you can see here that there's like not a dramatic change when you have like a really big patch or a really small patch. Like of course like when you get, and it's roughly all stays around like 100 degrees. And then like when you get to like really, really large patches, then they're like anomalies, but we'll talk about that later. And so we're like, okay, we saw there would be some kind of correlation between the patch size and the patch opening angle, but we didn't see any here for squares. So we're like really puzzled. And then we're like, okay, let's try to see what happens for triangles. Okay, so, but then for triangles, you actually see an upward trend. So as you increase the patch sizes, that the patch opening angle also slightly gets bigger. Like we do see a large spread in all this opening angles after optimization. So we want to kind of like, we first want to see like, are these optimization results real? And then also ask the question that, okay, why is this happening? And another thing I really want to note is that even though that you see like a large spread of like the patch opening angles between triangle and squares, that there's like not a lot of overlap until you have like a really, really large patch size, which is almost the size of your center particle. So which still says that even though there's a large spread, there's still a nice separation between triangle and squares, which means that this model can still like successfully separate out like a design that will predominantly form triangles and a design that predominantly form squares. And here kind of just like to show you a few examples of them actually like all assembled despite like the sizes of like their patches. Okay, so kind of like we see some like correlations in all these optimizations, but of course like we now like the data is kind of noisy, and then we want to see like is there any way for us to make the data less noisy. So one thing we did is that instead of like all this like directly self-assembly designs, we just want to first ask like what happens if we want to just like stabilize a triangle or a square. So now instead of having like a simulation of many particles, we're just going to have a simulation of like 3 or 4 particles. And then we're going to bias our simulation at the beginning to have them like for the positions of the triangles to or squares to be already at our desired place. But we're going to like randomize the rotation to kind of make sure that because like we're starting from like a random guess, so like the rotation is something that we cannot really control to know like whether it is already correct. And so hopefully during optimization that at the end, it will go something that they will find the correct rotation and then also where the correct opening angle. Okay, so we did a bunch of like simulations, optimizations for different patch sizes again. And so here's the result for triangle stabilization. It looks like even messier, but let me break this plot for you. So actually we can divide this into 3 regions. So here we have like this like really weird behaviors because we only have 3 particles. So like they're naturally self-limiting. You will not see this in self-assembly because this was like growing indefinitely. That is like not our design. And then here we have like the sort of like the desired morphology we want. And then here is kind of like, especially in large patch sizes, that this is kind of like a more space filling like patch where like all 6 patches is like all jump into the middle and then act as one thing. Okay, but if you look at like the desired one, so for triangle stabilization, that the desired morphology, like the results are quite similar compared to the self-assembly one. So what happened to squares? Okay, so squares shows something completely different. So here we see this like really nice bifurcation of like the patch opening angles for squares. That is, and if you go to the limit of where the patch size is going to be go to 0, so like a point patch size, you can kind of see that you will actually go to 90 degrees. And here are some structures for like the small patches and the big patches. So this kind of like gave us, so even though we're using the same model and literally the only thing separating out between assembling a triangle and a square here is like the patch opening angle. But we see completely different optimization behaviors of correlation between when you have like a small patch and a big patch and like how the patch opening angle behavior happens. So we're kind of really puzzled by this. And then we keep looking at this like 2 different finite structures. And we realize that is the triangle structure, they're actually rigid. And the square structure, they are floppy, which kind of like means that by having this like offset of the patch opening angles, that they are able to like maximizing their vibrational entropy, which is something that you will not really be able to predict, like if you're not allowing your particles to actually having the kinetics and then like evolving in the simulation. So to kind of demonstrate that that is actually what's happening, that we measured the interior angles of like square clusters and triangle clusters, and you can see that for square clusters there is a vibration between like up to 10 degrees. So it is really a large like breathing of these clusters, while the triangle interior angles is only 1 degree of like the 60 perfect 60-degree angle. Yeah. So this kind of really gave us like a really nice way to not only find out like what are good patch opening angles for assembling this like structures, but it also kind of like told us a kind of like new physics of thinking about mapping between a parameter set or like the interaction between different design parameters into the final structure you're forming, how like the properties of the final structures can really play a role on like the interplay between all these different design parameters we can do. And to kind of map this into like a more applied sense, this can also tells us that if you're if your synthesized particles and your goal is to assemble a floppy structure at the end, then you really need to make sure like the location of your interaction sites are precise, while the size of your interaction sites can kind of like vary a little bit more. But if you are wanting to assemble a rigid structure, then you really want to make sure that the combination of your the size of the sites and then also the location of the sites have like a good one-to-one mapping. Okay, so this is kind of like here I'm only talking about the kind of like the patch opening angles. And then one question we had like a lot is why there's like so much degeneracy in all this like patch opening angles at the end. So one thing I haven't really told you is about the binding energies. So this is like something that is like really ongoing. And then kind of like one thing I can show you at the moment is that the dependency of binding energy compared to the patch opening angle. So you can see that our binding energy is like from the simulation is like really going like all over the place. And then our like naive call of that you want to have like really, really weak AA and BB binding only happens like it's not like the best solution we have here. So like a lot of time is that you see you almost have like on par on target and off target binding, and but then you're still be able to like do all this like optimization. So this is kind of something like we're really fascinated about it right now, and then like doing like a lot more measurements and analysis on like our optimization. But kind of like as a final thing, I want to show you is that one thing we're learning is that having no crosstalk, so like here is like the AA and BB binding might actually not be very good for our self-assembly. So here we're going to like, so AB is our on-target binding and ABB is off-target binding. So I asked like one of my high school student, amazing high school student, to do a lot of forward simulations to measure the assembly speed of squares. So here we're showing, so our AB binding is going to be 17. That does not change. And then we change the A and BB binding from like 0 to 17. And so one really striking thing we found is that having like an intermediate off-target binding energy of 10 actually allows us to assemble our finite structure the fastest. So so this way kind of like really breaks all my intuitions of like crosstalk is bad. And so kind of also paying homage to biology and like nature systems is that we also always know that nature has this really amazing way to kind of like use noise like to do something good. So this is like an exciting direction like I'm really looking forward to explore more. Yeah, so at the end I just kind of want to sort of like wrap up and then how like hopefully like in this talk I convey the idea that we can use like inverse design as a learning tool and to learn more physics. So here kind of like we build an inverse design framework for soft material assembly, and this framework not only help us to accelerate material design but also help us to uncover fundamental rules for self-assembly. And so lastly, I want to acknowledge like all the software use, the compute resources and the funding resources. And thank you so much for your attention.